Okay, so we start chapter 4. We're at a good spot. We can really get through a lot of chapter 4. My guess is you'll probably be able to even have a short little test here even before break. We'll cover these first 3 sections very quickly. Nice little short test. That's what I've generally done the previous years because this is generally where we leave off. But we want to talk about these interesting points right here. Now, last year you guys had a test. Do you remember this test? This test on polynomials. I'll show you the inside of it, where you had to list the different sign changes and the different choices for rational roots theorem, all that stuff. That's all stuff packed away in your brain still, right? Okay, and you had to graph polynomials on the front. And the question was, how high or low does the polynomial go in between that behavior? You guys knew how to graph triple roots, double roots, things like that. But the question was, how high up do you draw something, or how low do you go? And that's really what we're going to talk about with what we call maximum and minimum values. And absolute maximum values, or global maximum, these are 2 different phrases sometimes books use, but absolute or global would be the largest value of a function over its domain. So if you look at the picture to the right, we're going to define the domain of this function. We'll say the domain is going to be from -3 to +4. So those are the only x values of the function by which we'll, describe its characteristics. What is the largest value that function attains over that given interval? 64. So 64 is what we would call an absolute maximum or a global maximum. Okay? I'll use those words interchangeably. What do you think is absolute minimum? Smallest, yep. What is the smallest value that this function attains over that given domain? Very good, -152. What are different about those points? One's obviously biggest, one's obviously smallest, but what is different about them? Yeah, one is at an endpoint. You can see right here that the global maximum is at an endpoint of the graph. And then the other one is it's not really an endpoint so much as it's part of the graph. The graph happens to dip down. And so sometimes absolute maximums or minimums, sometimes they happen at endpoints, and sometimes they happen in kind of this middle behavior, so to speak. Okay? Local maximum, or relative maximum, that is the largest value of a function in the immediate area. Calculus professors would hate if I wrote that, but it's all right. There's actual mathematical terminology that we'll use. We'll bring that up later on. Now today we're just going to use that as kind of a quick reference. So when I say immediate area, I mean you kind of circle an area. And in that area, if there's a kind of a smallest value, such that if you move to the left or if you move to the right, it's the biggest, then it's a local maximum. So for example, if I just circle this area right here, okay, if I pick this spot right here in the middle, if I move to the right, what happens to the graph? Does it go up or down? It goes down. And if I move to the left, the graph goes up. So it's really neither a maximum or a minimum, because as you pick this spot here, as you move to the left, it goes up. If you move to the right, it goes down. So there's really no, it's not the biggest value around it, and it's not the smallest value around it. But notice if I just switch my immediate area to say right here, let's see. If I move to the right, the graph goes. If I move to the left, the graph goes up. So in that immediate region right there, this would be the smallest value. So it is the local minimum or relative minimum. This one would be what we refer to as a local maximum. So the local maximum value is going to be 37. In this immediate region, that's the biggest value, because if we move to the left, the graph drops. If we move to the right, the graph drops. Okay? Yes, you can. And so for this part right here, as we define local minimum, we would say smallest value of a function in the immediate area, and we would have two of them. What are they? We don't really say that local minimums and maximums happen at endpoints, but globals can. Is it possible to be a local minimum and a global minimum? This is an example of a spot that's a local minimum and a global minimum. So that is possible to happen. If you think about simply a parabola that goes upside down, is that a local maximum? Is it a global maximum? Yes, it's both. And same thing if we draw it the other way, it is both a local minimum and a global minimum. So that's the terminology for today. You got that? Okay. All right. Then we get to a man by the name of Fermat. It says, looking at the graph provided, identify absolute maximum, minimum, as well as local maximums. We already did that, correct? If f has a local maximum or minimum at C, and if we got it is what I thought it was. And if f prime of C exists, then f prime of C equals 0. So let's use Fermat's theorem. Look at my shape. Okay? Here's what Fermat's theorem says. Okay? Let's circle a spot. Is that a local minimum? It is. Can I take the derivative at that spot? Yes. So, therefore, the derivative must be 0. Very good. Let's try a different one. Okay? Is that a local maximum? Yes. Can you take the derivative at that spot? Yes. Therefore, the derivative is 0. Is that a local minimum? Yes. Can you take the derivative of that spot? No. Right? It's a corner. The derivative from the left is not the same as derivative from the right. So therefore, we can't talk about it. Is the derivative of this equal 0? No, you can't even take the derivative of it. Okay. Okay, so what if I do this? Okay, here's another one. What if I do this? I want to focus on this spot right here. If I took the derivative right here, what would I get? 0. But is it a local maximum or minimum? No. So just because the derivative is equal to 0 does not mean that it is a local maximum or minimum. Fermat's theorem says if there is a local minimum or maximum, and if it could take the derivative, then you're going to get 0. And that's an important thing. So that's what we're going to utilize. And that's pretty obvious, you guys. A critical number of a function, f, is a number c in the domain of f such that either f prime of c is equal to 0, or f prime of c does not exist. Okay? So, you know, using Fermat's idea, it's like, well, hey, if we want to find those spots, so like I showed you guys the graphs right here, if we want to find out how high or low they go, we should just take the derivative and set it equal to 0. But he also says, you know, part of it is like, we also should look for where the derivative does not exist, okay? So, let's look at examples of critical points, okay? Here's one good example, okay? If we, you know, we're looking for the critical points on this function, where would they be? minimum and at the maximum. If you were looking for critical points, you would find these spots. And they tell us about the shape of a function. And that's where f prime of c would be equal to 0. And this would be, say, c sub 1, and this would be c sub 2. Those would be the interesting points of the function. So that's what we're going to try to find. Can you give me an example of a function that's undefined somewhere? A vertical line, a circle. How about a function that looks like this? Y equals 1 over x. Do you remember what that graph looks like? So where's the interesting spot that we have to check here? Where is the derivative undefined? 0. F prime of 0 does not exist. The function cannot be evaluated at that spot. So we would be trying to find the value 0 for this function. That's an interesting spot for us where it's undefined. Can you give me an example of a function that has a corner? Absolute value of x, okay? As you look at that function, the function does exist there. You do have a spot, but f prime of c, again, does not exist. If that was, say, a c value. Because you can't take the derivative of it at a corner, because the derivative from the left is not the same as the right. And finally, a vertical tangent. That's the other spot where we got to be careful of. Here's a function that I could draw that has a vertical tangent. Y equals x to the 2/3 power. You can see, true or false, the derivative of that function is never negative. True, yeah. Yep, if you draw the slope, it's always going to go up. And for one moment right here, right at this spot, you can see you have a vertical tangent. And therefore, f prime of c does not exist. We've seen those examples before, right? That's where the derivatives did not exist. So all we're adding to our examples is this minimum and maximum where the derivative is equal to 0. Everybody okay with that? Okay. Now we get to try the problems. You guys will be great at this because your algebra skills are awesome because you had such an amazing algebra teacher. Anything else? Oh, wow. Wow. Don't utter her name in this classroom ever again. Do you think teachers should exchange Christmas presents? How about birthday presents? Well, my birthday's in December, and I told her she should get me a birthday present. Her birthday's in June. I said, tough luck. I don't think there's anything wrong with that. Do you? Exactly. Tyler says no. So no. Who cares? All right. So send her a card in the mail. It's kind of creepy. All right. It's like showing up with a bag of candy or something like, here you go, happy birthday. That's not creepy. Send her a card. No, I don't. But my birthday is coming up, and I'm gonna bring you guys treats. Okay. Oh, a gift card. Somebody gave me a gift card a while back ago. It had 2 cents on it. And so, I think I actually used it too at a gas station. They thought I was really strange. I was like, well, it's got 2 cents. They said, why don't you just throw it away? Throw you away. All right, so, here we go. Find the critical numbers of the function. Is this function ever undefined? No. This function is defined for all real numbers. Okay? It's defined everywhere. Okay? So I'm just going to go ahead and take the derivative. F prime of x is equal to, what's the derivative? Excellent. Now, I look at the derivative. Is that ever undefined? No. So our critical values are never going to be where the derivative is undefined or the function is undefined. That's not going to happen. Okay? All we have to do then to find the critical numbers is set this equal to 0 and factor it. What is it factored to? 3x minus 1 and x minus 1. So find the critical numbers of the function. Critical numbers are x equals 1/3 and 1. Do you think there's a good chance that those are local maximums or minimums? Do we know for sure that they are local maximums or minimums? Not yet. Okay? We are taking the first derivative. I will teach you later on how to take a second derivative and how that can actually tell us whether or not it's a local max or min. But we'll get to that later on. Let's look at this function from the beginning. Okay? The second function. Is this function ever undefined? It sure is. It is definitely undefined at 0. So I would expect that when I take the derivative, it would also be undefined at 0. So let's just make sure that happens. I would like to change the function. Everybody okay with that? I divided both parts by x. Reducing parts is if you just, divide one side. So all I did was factor an x out. I didn't want to use the quotient rule was really the deal. Yeah. So this is the same as x minus x to the negative 1. Very good. F prime of x. What's the derivative? One plus 1 over x squared. Bring the 1 down, subtract 1. Okay, so I have this. Where is this undefined? 0. So I have a critical point at x equals 0. That's one of them. Okay, we know that that's where the derivative is undefined. Now what we will do is we'll find the other ones by setting the derivative equal to. So 0 equals 1 plus 1 over x squared. Subtract the 1. Negative 1 is equal to 1 over x squared. Any ideas? Multiply both sides by x squared. Negative x squared is equal to 1. Divide by negative. X squared is equal to negative 1. X is equal to plus or minus I. So is there any solution for where it's equal to 0? No. So my critical point is only where the derivative is undefined. There is no point at which the derivative is equal to 0. So you tell me, does this function have a local maximum or minimum? No. In fact, let's graph it real quick so you can see for sure how this looks. Anybody know what time we get out of here? 11:11? Because if I plug in 0, I get 1 over 0, and that's, you can never have 0 in the denominator. Come on. Open up. What is the problem? X squared minus would you guys agree by looking at this that the derivative is never equal to 0? Can you see that it's undefined as 0? So therefore, our algebra confirms it. That's what we want to do. Let's try the next one. Absolute value of 3x minus 6. Oh boy. What about that one? Yeah, it's that kind of shape. Okay? It looks like this. Okay? Now, let's solve the inside equal to 0. 3x minus 6 is equal to 0. X is equal to 2. So that tells me that it's horizontally shifted how many units? 2 units. So this graph looks like this. Okay? Where this is 1, this is 2, so on and so forth. Anybody want to guess what the slope of the function is right here? Three. How about this side? So I'm not even going to do any algebra here, really. I'm just going to look at the function, okay? Is the derivative ever equal to 0? No. Is the can you take the derivative at 2? No. So my critical point, x equals 2. That's it. Critical point is where the derivative is equal to 0 or the derivative does not exist. And we can't take derivatives at corners. We can't take derivatives where it's undefined, like at 0 here. So that's why we're concerned. Okay. And the last part, okay? We won't do the closed interval method. We'll talk about that tomorrow. We'll do this last problem right here. Here we go. Sorry. So we have x to the 3/2 minus 2x to the 1/2. That's our function. Do you know anything about that function? If you don't know it, you could graph it ahead of time and see if there was a spot where, it didn't exist, where you couldn't plug stuff in. As we graph it, if I plug this in, x to the parentheses, 3/2 minus 2 square roots of x. And if I graph that, look at what I get. Where does the graph start? It starts at 0. Let's look at y. Okay? Can you take the square root of positive numbers? Can you take the square root of 0? Yes. Can you take the square root of negatives? No. So if you plug in a negative value for x, you would be taking the square root of a negative here and of here. So this is not part of its domain, okay? So you can't take the derivative at a corner. So what would be the endpoint of this graph here? Where would it have an endpoint for what x value? What's the last x value you could plug in? 0. So we already know that 0 is an endpoint. So therefore, we are not going to be able to take the derivative at that. And that will show up as we do this problem. So let's take the derivative of this graph. You can get a visual for what it looks like. Let's take the derivative. What is the derivative of x to the 3/2? 3/2 x to the 1/2. So very good. You said 3 roots of x over 2. Exactly. What is the derivative of negative 2x to the 1/2? Yep, negative x to the negative 1/2, or agreed? When you drop down the 1/2, it stays minus 2. Okay? Look, what value can you not plug in for x here? 0. So you know already you have a critical point at x equals 0. Let's look at our graph ahead of time. Does it look like the graph has a spot where if you take the derivative, you get 0? Yeah, looks like really close to the beginning, doesn't it? So if we set this function equal to 0 and solve, hopefully we should get that spot. Let's try that. I'm going to create just a little extra room here. 3 roots of x over 2 minus 1 over the root of x. equals 0. Okay? How would you like to do it? Okay? 3 roots of x over 2 equals 1 over the root of x. We sure can do that. I'm going to put forth a suggestion, you guys. What? Yeah. Be very careful, everybody. Right now, the degree of this equation is 1/2. Anytime we increase the degree of the equation, we have to be careful that we possibly added a solution. Okay? We have to be careful of that. So, we cross multiply. You get 3x is equal to 2. Divide by x is equal to 2/3. Let's see if that fits within our graph. I'll zoom as a box here, and we can see. There's my graph. I'm going to trace it, and I'm going to go to, just gonna go trace, and I'm going to go to where I think it's about 0. And does that look like it's about 0.67? 0.68? Here's a way we could check. Watch this. Second, calculate. Number 6, dy dx. That tells me the rate of change, right? I select 6, and I plug in 2/3. 2 divided by 3. It's going to tell me the slope at 2/3. Negative 4.5 times 10 to the negative 7th. About what value is that? 0. That's negative 4.5 times 10 to the negative 7th. So that's negative 4.5. That's 1, 2, 3, 4, 5, 6, 7, right? Bunch of zeros in there. Okay, so that's a very small number. That's what your calculator was able to compute. That's the approximate slope, so we know the derivative is equal to 0. So therefore, we have, as you see right here, critical points of 0 and 2/3. 0 is an endpoint, 2/3 is where the slope is equal to 0. So today, your objective was to be able to identify global and local maximums and minimums, and to be able to then find the critical points of a function. We'll pick up with the rest tomorrow. You'll have some time to work. I'll put your assignment on the board for today. Yep. Numbers 31 through 38. Okay. That's it. All right, you'll have the rest of your assignment for this tomorrow.